In Chapter 2 of Integral Calculus Theory, we'll be studying differential equations. In Section 2.1, we're going to be modeling situations with differential equations. Now, before we can do anything, we have to figure out what is a differential equation. Differential equations are equations that involve x, y, and the derivatives of y. For example, y double prime plus 2y prime equals 3y would be a differential equation. This is the same differential equation, just using f prime notation. And this is the third way of writing the same differential equation, just using the d squared y dx squared and the dy dx as our second and first derivatives. So today we'll be interpreting verbal statements that represent differential equations. Before we can start writing differential equations, we have to recall a couple of things. First of all, direct variation. If y varies directly with x, or if y is directly proportional to x, we can write the proportionality statement as y is directly proportional to x, and we use what's called an alpha symbol to show that relation. To change this to an equation, you get rid of the alpha, put an equal sign, and you add a constant. So if y is directly proportional to x, we're going to get an equation y equals kx. Similarly, if y is inversely proportional to x, we can write it as a proportionality statement as y is proportional to 1 over x, and as an equation, it would be y equals k times 1 over x. So the equal sign and the k replace the proportionality symbol. We write our equation. All right, question number 1 says, Catherine runs around a linear path. Her position is given by the function pt, where t is measured in seconds since she started running, and p is measured in miles. During the first second of her run, Catherine's acceleration is proportional to the cube root of the time she started running. Write a differential equation that describes this relationship, where k is the constant of proportionality. Okay, well, they tell us that position in this particular case is p of t. So velocity is going to be the derivative of position with respect to time, and acceleration is going to be the second derivative of position with respect to time. Now, to write this statement as a differential equation, it says Catherine's acceleration, which is d squared p over dt squared, is proportional, so equals k to the cube root of t. So k times cube root t. And that would be your differential equation. Okay, example 2 says bacteria in a certain culture increase at a rate proportional to the amount present. So again, proportional to the amount present, that's the phrase for a differential equation. If the number of bacteria doubles in 3 hours, how many hours will the number of bacteria triple? We write a differential equation that describes this relationship where k is a constant. Okay, so again, bacteria would be b, rate means derivative, proportional, that's our constant k, and to the number present is going to be b. And we want to write a differential equation that describes this relationship. So the rate change of the bacteria is directly proportional to the amount present. So it's going to be equals constant k times b, the original number present. All right, this example, it was an actual AP multiple choice question, and it asks us that, it talks about a rumor being spread amongst the population of n people at a rate proportional to the product of the number of people who have heard the rumor and the number of people who have not heard the rumor. If P denotes the number of people who have heard the rumor, which of the following differential equations could be used to model this situation with respect to time, where K is a positive constant? So N is the total number of people, okay, and P is the number of people that have heard the rumor, okay, and we want to know that a rumor spreads amongst the population of n people, so that would be dp dt would be the number of people who've heard the rumor, okay, at a rate proportional to the product of the people who've heard the rumor, p, times the people who have not heard the rumor, which would be the total number of population, minus P, which is the people that have heard the rumor. So that translates into B. Okay, I want you to pause the video and give this one a try. Okay, hopefully you've had a chance to try this one. The rate of change of A with respect to T is proportional to R. So the rate of change of A with respect to T is dA dt is going to be some constant K times R. That one was pretty straightforward. All right, there's a couple more here we're going to practice with. So this one says that the rate of G with respect to T is proportional to the square of G. So the rate of G with respect to T is dG dt is going to be my constant K times G squared. The rate growth of a population of zombies over time is proportional to the population of zombies. So dZ dt is going to be equal to K times Z, which is the total number of zombies present. The rate change of J with respect to time is inversely proportional to the square of J. So J dt inversely proportional is going to be K over the square of J. And there would be your differential equation. This one here says in a community of F farmers, the number of farmers who own a certain combine changes with respect to time at a rate jointly proportional to the number of farmers who own the combine to the number of farmers who do not own the combine. Okay? So, in this particular case, dx dt, x is the number of farmers who own the combine, is going to be the constant. X, the number who have owned it. Jointly means product. With the total number of farmers minus X, that represents the number of farmers who do not own the combine. All right, I'd like you to pause the video and give this one a try. Okay, this one's very similar to the one prior. It says, suppose a virus is spreading in a network of computers. There are M computers in the network. The rate of change in the number of infected computers is jointly proportional to the number of computers already infected, J, and the number that are not infected. So dJ dt is going to be equal to some constant of J times M minus J. The rate level of response R with respect to the level of a stimulus S in a joint is a joint proportionality between the level of the response and the inverse of the level of the stimulus. This differential equation is known as Bertano-Stevens law. So R ds, so the rate change of R with respect to S, is a joint proportionality between the level of the response and the inverse of the stimulus. So it's going to be K, the level of the response, divided by S, which is the inverse of the stimulus. Barometric pressure, okay, P measured in millibars, changes with respect to altitude A measured in feet above sea level at a rate that is directly proportional to the altitude. So dP dA is going to again be some constant times A, which is the altitude. All right, so that pretty much ends the first part of 2.1, which is modeling differential equations. So there's a handout that is part of your assignment, so I'll give that a try and we'll talk about those answers in class.